Welcome back to the Fundamentals of IPOS. This is session number 3. We're going to step away from learning the C programming language for one session to talk about numbers. So this is a brief numeric detour. Numbers are very important in the world of IPOS, and you really need to understand how they're implemented within the programming language and the MoviDrive B. Now, of course, as human beings, we typically use the decimal number system, which is based on powers of 10. 10, 100, 1000. You can see you're increasing by a factor of 10 every time. Or in the fractional side of things, 1/10, 100th, 1000. We're again increasing in fractional powers of 10. Decimal works well for everyday life. But in the controller world, which includes the MoviDrive B, it's not always the best system. Almost all programmable controllers require some familiarity with the binary and hexadecimal number systems. These number systems work better than decimal in a control environment since all control scenarios involve working with individual bits. We use bits to do things like turn a motor on and off, initiate an operation, communicate with an I/O device. So bits are really just part of the control world, and binary and hexadecimal are just better number systems for that. Now, even though these systems may seem strange to you if you've never worked with them before, they actually work almost identically to the decimal system we've used all our lives. You just have to see past the strangeness a little bit. So let's look first of all at how binary works. Binary is a very simple number system because it has just 2 symbols. Now in the world of decimal, we have 10 symbols, 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. And we use these to represent numbers. Well, in the binary world, it's much simpler. We have just 2 symbols. We have a 1 value, the first quantity, which is 1, and a nothing symbol, which is 0. And that is it. By combining lots of zeros and ones, we can produce numbers of absolutely any size. We arrange those symbols in columns, just like we do in the decimal world, and we go from right to left with 1 symbol per column. So something like this. Typical binary number. We call the lowest bit, the one on the right, the least significant bit, or LSB. And we call the top bit, the one on the left, the most significant bit, or MSB. By the way, we do this in decimal too, but we don't call them bits. We call them the least significant digit and the most significant digit, and it works the same way. The one on the right is the least significant, the one on the left is the most. Now the first column, the least significant bit end, simply tells us how many ones are in that position. So you can either have a single 1 in there, or you can have a 0. So there's either no ones in there, or there's 1 1. And that is it. The second column has double the value. It's called the 2's column. So if there is a 1 in that position, it means we've got a 2 there. And if there's a 0, of course, we don't. The next column doubles its value again. It's called the 4's column. And if you have a 1 there, that means there's a 4 in that position. In this example number, there's a 0, so that means there are no 4's here. And then we continue doubling however large we need to go. So the next would be 8. If we had another column, it would be the 16's column, then the 32's, 64's, and on it goes. You can go as big as you need to go to accommodate whatever size number you're trying to produce. Now to find the decimal equivalent of a binary number, it's really easy. You just add the column values of every column that's got a 1 in it. And if it's got a 0, just ignore it. So in this case, the 8's column has a 1, the 2's has 1, and so does the 1. So you add 8 plus 2 plus 1, and that is 11. That is the decimal equivalent of 1011. Pretty simple. Now, there's an even simpler way to deal with binary numbers, and that is to use a calculator app that can work with other number systems besides decimal. This is the one that comes with Windows, and if you change it to programmer mode, it supports all the number systems that programmers typically use. So this is what I recommend you do. There's really no virtue in doing things by hand just to say you can do them by hand. Use the calculator to deal with numbers and you're good to go. And of course, what you might want to do is get a calculator app for your phone that has a programmer mode as well. And that would let you work with numbers very quickly wherever you are. However, that said, let me give you a little tip. All programmers should memorize the first 16 binary values, and you'll see why in just a minute. It's not that hard to memorize 16 values. Once you get the pattern under control, it's pretty obvious, and it will pay big dividends. So these are the first 16 binary numbers 0 through 15 in decimal. 4 bits per binary number. If you just memorize these, and as I say, look at the pattern, you can kind of see how they work. That's going to help you do almost everything you have to do in IPOS. So I encourage you to memorize these if you don't know them yet. Now, hexadecimal, which is also called base 16. It's a number system based on the number 16. Let's look at this, and you'll see why we use this kind of odd number system in programming in computer and control environments. Binary numbers get ungainly very fast because you need to have a lot of bits to represent even relatively small numbers, and all those zeros and ones eventually start to dance before your eyes. So, many programmers prefer working with hexadecimal numbers, and the reason they do is because it's very easy to convert back and forth between hexadecimal and binary. The two number systems were almost matched with each other. Now, a hexadecimal number has 16 possible symbols. Remember, binary has only 2, decimal has 10, hexadecimal has 16. You may wonder, where do we get those extra symbols? Well, we do something a little strange. We use the familiar 0 through 9 for the first 10 possibilities, and then we use the letters A, B, C, D, E, and F for the remaining numbers. So hexadecimal numbers often have letters in them. That's kind of how you can spot them. And there's no reason you can't do that. Maybe your kindergarten teacher would have thought it was strange, but they're just symbols after all, and they represent different numeric values. Again, I encourage you to memorize the first 16 hexadecimal values as well. So really, this is the chart you should memorize. It's got the decimal numbers 0 through 15. It's got the binary numbers that are the equivalent of 0 through 15. And then it's got the hexadecimal numbers 0 through 9, and then A, B, C, D, E, and F. If you just learn this little table, that's really all you need. So let me show you how to use the table to convert back and forth. It's really easy, kind of fun. You can convert between binary and hexadecimal in your head once you memorize these first 16 values. Here's how. Take the binary number that you want to convert to hexadecimal and group it into 4 bits, moving from right to left. So we have a number here, it's got 7 bits in it. Break it into groups of 4, just like this. Now, you notice that second group only has 3 bits in there. So if there aren't enough bits to give you 4, just add an extra 0, like that. And now, look at your table and convert those patterns of 4 bits to the equivalent hexadecimal value. Okay, we start with the bottom 4 bits, 1011, and we look at the chart and we see that those correspond to the hexadecimal number B. Then we look at 0, 101, find it on the chart, that's equivalent to 5. So the hexadecimal equivalent of 0, 101, 1011 is 5B. Really simple. And once you memorize these, you can just look at the bits, write them down, you're done. Converting the other way is just as easy. Convert each hexadecimal symbol into 4 binary digits, 4 bits, again using the table or once you've memorized it out of your head. the binary groups should be in the same order as the original hexadecimal number. So if we have the hexadecimal number 1F8B, just convert each one of those symbols into its matching binary pattern. So B turns into 1011, 8 turns into 1000, F turns into 1111, and 1 turns into 0001. That's it. Super simple. So let's do a practice activity. What I'm going to do is give you some numbers to convert, and what I'd like you to do is pause the video on that screen, convert the numbers, preferably using that table I showed you, and then when you're done, unpause, and we'll go ahead and check your answers. So here are the numbers. I'm going to give you 4 binary numbers to convert to hexadecimal and 4 hexadecimal numbers to convert to binary. So please pause the video and unpause it when you've done your conversion. Okay, let's see how you did. Binary number 101000101 is the equivalent of A5 in hexadecimal. 011111 is 1F in hexadecimal. And the next number, which has a lot of bits in it, so I'm not going to read them, is the equivalent of C372. And then finally, your last one is 6E9D. So hope you got those right. Now let's do the hexadecimal to binary. We'll take 5C, convert it to the binary number, and it's 0101 1100. Hexadecimal 10E9 is 0001 0000 1110 1001. 3D is 001 1101. And 26B4 is 001 001 1010 110 100. Hope you got them all right. If not, make sure you understand what you did wrong. And let's move on. Last thing we have to talk about is how we encode a sign in numbers when we're dealing with binary or hexadecimal. We don't put a plus or minus in front of them like we do in decimal. Now, all the numbers we've just been playing with were unsigned. In other words, they weren't positive and they weren't negative. They were simply what we call a magnitude, a number that represents a certain size. And many programming languages can work with unsigned numbers. But IPOS is not one of them. In IPOS, everything pretty much is treated as a signed 32-bit number. So we need to understand how the sign works. If you don't, you can make some big mistakes and really mess up your numbers. Signed numbers follow slightly different rules than unsigned as far as how we work with them in binary and hexadecimal. And you have to be careful because some numeric operations behave differently with signed numbers than unsigned. Happily with IPOS that doesn't come up too much, but you should still be comfortable with the difference. Signed numbers are created using a system called 2's complement notation, which sounds really fancy. Mathematicians think it's really clever. Actually, it is kind of clever. But don't let the name throw you. It's actually relatively easy. Let's look at how it works. All signed numbers have what is called a sign bit in the most significant bit position. It's an extra bit we put in there to indicate positive or negative. So it's at the top of the number on the left side. So if there's a 0 in the MSB position, it means it's positive. And if there's a 1 there, it means it's negative. And that's it, right? No, sorry. It would be lovely if it was really that simple. but it's much more complicated. After all, this is a computer system. What do you expect? All right, let's see how it works. Positive numbers are actually very easy. Here's what you do. If you want to take an unsigned number and make it signed and make it a positive signed, all you do is you attach a 0 bit to the most significant bit end. So if we have this binary number, 1101001, which is 105 if it were a decimal number, if we want to make that a positive number, then all we do is we put on that 0 sign bit, and now it's plus 105 in binary. Really simple. Okay, that's not bad. Now, if we need to have our number a specific number of bits, like 32 bits, for example, which is what IPOS wants to work with, we have to do what's called sign extension to expand the number correctly to the specific size. And the way we do that is we just duplicate the sign bit as many times as necessary to give us the bits we want. So if we want a 32-bit number, here's what we do. That blue sign bit gets duplicated a bunch of times, and all those are actually sign bits. They're copies of the sign bit. And you may think, well, can I just drop those? After all, leading zeros are really not important. And the answer is absolutely not. The sign bit is sacred, and if you extend it and you have multiple sign bits, those are sacred. You can't drop it without the number turning into something else. If you drop those blue sign bits, you would actually now have a negative number, which is definitely not what you want. So don't mess with the sign bits, just leave them alone. They have to stay there. All right, that said, negative numbers are a bit harder. How do we create a negative number? Well, we start out the same way. We take the unsigned number and we put a 0 sign bit on the most significant bit end. So again, we'll take 105 decimal, an unsigned number, and we put on the 0. Now that gives us a positive number. It's now signed, but it's got the wrong sign. It's the positive sign, not the negative. So that's plus 105. How do we make it negative? Well, we do 2 steps. First of all, we invert or just flip all the bits so they're the opposite value. So if it's a 0, we make it a 1. If it's a 1, we make it a 0. So here's our number. We've just flipped the bits, and you also flip the sign bit, you notice, the blue bit there. So that's step 1. And now we have to do something else. We take that inverted number, and I've got the same number here, and we increase it by 1. We add 1 to it. Sort of like this. We do this like an addition problem like we learned in grade school. Just add up the columns. If there's a carry, move it into the next column. So there we go. That's our number increased by 1. So it is 1001, 0111. And that is now a negative number. It is minus 105 if we would convert it back to decimal. So that is how you make a negative number. So it takes those 2 extra steps. Yes, it's a little weird, but it actually is rather clever and it works very well. Again, if we need to make this fit a specific size, like 32 bits, we use sign extension and we, again, duplicate the sign bit. Just like that. So that single 1 sign bit gets replicated a bunch of times, and those are actually all signs. And yes, they are sacred too. You can't get rid of those. If you get rid of them or fiddle with them in any way, you've corrupted your number. Now, one final point. If somebody just hands you a binary number, you can't know if it's signed or unsigned just by looking at it. They have to tell you what it is. It could be an unsigned number, just a magnitude, or it could actually be a signed number with a positive or negative sign bit. You need to know. With IPOS, of course, we can generally assume that all IPOS numbers are signed, which makes life a bit easier. So you look at a number, and if it's in binary, if the most significant bit is 0, it's positive. If it's 1, it's negative. What about hexadecimal numbers? How can you tell with them? Well, it's easy. If the top digit is 0, 1, 2, 3, 4, 5, 6, or 7, it's positive. If it's 8, 9, A, B, C, D, E, or F, it's negative. Just remember that, and you'll be okay. Now, everybody needs to do this just once. And no, I don't mean skydiving, but this is kind of the skydiving equivalent that we will do with numbers. Everyone should do a conversion into plus and minus once, just to say they've done it. So let's do it. Again, we'll do this as a practice activity. You can pause the video, make an attempt, then unpause it, and I'll step through it and you can see how you did. So here's what I want you to do. I want you to take this number, which is 83 in decimal. It is 1010011 in binary. And I'd like you to make that into plus 83 and minus 83, and then sign extend it so it's a 16-bit number. All right? So go ahead, pause the video, do those two conversions. All right, let's see how you did. Let's do the positive number first. Remember, we just add a sign bit onto the end, and then sign extend it till we have 16 bits. So this is 83, and it's now actually positive 83 in binary. So it should look like that. If you got that number, you did great. Now that was the easy one. Let's do the negative number, which is a little more challenging. So we'll start again. We'll take 83 decimal and its binary equivalent. First thing we'll do is we'll make it a positive number. So we add that sign bit onto it. So it's now plus 83. Then we flip all the bits, including the sign bit. So we invert them to the opposite condition, and you can see it right there. 10, 10, 11, 00. And then increase it by 1. So we add 1, so we put a 1 underneath there, do an addition problem like you learned in first grade. And here's our number now, 10101101. That is actually now our negative 83. But we have one more step. We have to sign extend it so it's 16 bits. So we add a few more ones on there. We take that blue bit and extend it out. And now it is, in fact, minus 83 if we turned it back into decimal. Okay, hope that made sense. You won't have to do this again, but I wanted you to try it once. And the reason is, of course, the smarter way is to use a calculator app, like the one in Windows. It can also do the sign encoding for you automatically. And I'd recommend you do that just because you're less likely to make mistakes and it's quicker. So how do we set up the calculator to do this? Well, of course, first we have to get into programmer mode. And then you need to click right here where the arrow is pointing until it changes to D word. That means double word. And that will limit the results to 32 bits, which is what we want in IPOS. Then you key in the decimal number just using the number pad. Select the sign using the plus or minus button on the screen. Don't use the one on the keyboard, use the one on the screen. That'll set the sign. And then you've got your hexadecimal and your binary equivalents shown there along with decimal. There's also something called octal, which is a number system that isn't used a whole lot anymore. And that is it. Little warning here with smaller positive numbers, they won't be sign extended to 32 bits. You'll have to add those extra zeros yourself to get 32 bits. But the negative numbers will always be exactly 32 bits long and properly sign extended. It's just the way the Windows calculator works. All right, well, that was a quick detour through numbers, and I hope it made sense. That is the end of session number 3. And in session 4, we will go back to learning about IPOS programming, enriched by our ability to work with binary and hexadecimal numbers.